All right, I think we're going to go ahead and get started. There's plenty of room up front if you want to get close to me. You don't have to. OK, so let me start with a quick show of hands. Who here is a software engineer? You write software all day, every day. Great. It's a good start. Of you, how many people have heard of Finagle? OK, that's another good start. How many people use Finagle? A bunch. Excellent. How many of you are on call in some way? When things break, you get paged. Yes. OK, you're my friends. How many of you have been in an incident in the last month where you have been paid for something? OK, some of you have had sleepful nights. That's great. How many of you have been woken up for some reason because of a computer? Excellent. OK, this talk is for you. You're my people. The rest of you, you're welcome to stay. But so my background is I started at Twitter in 2010. I started in the ops team as one of the first software engineers in the ops team. And my first on call, I was ops on call for all of Twitter.com. And I was woken up at 2 a.m., 4 a.m., 6 a.m. for things I didn't know how to fix. And if I'm being 100% honest, the first thing that went through my head was I could just quit. I don't have to wake up. I could just go back to sleep. And I didn't. And I thought that every other time I was woken up for the next 4.5 years, and I didn't quit for those reasons. And then things got a lot better over time. And so this is the story of how things got better from my point of view. So there's a lot that you probably understand with Finagle and from a programming model, but as an operator, I think there's a lot of value that isn't widely understood or talked about enough. And so I want to talk about, first of all, how it was to work at Twitter in 2010. Then I want to walk you through a number of the, I think, more novel failures we saw, which might help give some insight into why we made some of these decisions. And then finally, I want to introduce you to Linkerd, which is a project I've been working on for about the last year. All right, 2010. Let's all get in a time machine, go back to 2010. You don't have to come back if you don't want to. I understand. Who was on Twitter in 2010? It was a very different site, right? There were no pictures. There was a star you could click under tweets, but nobody knew what it did. You had to manually refresh the page. It was a very different product. And beyond that, it wasn't very reliable. One of the bigger events in 2010, is certainly one of the things that convinced me to join Twitter, was the World Cup. Anecdotally, there were a lot of engineers who were hoping for draws, 0-0 draws in the World Cup. Because every time there was a goal, the site would just fall over. And we saw a lot of this. And so Twitter was actually kind of famous for its failure, for its very visible public unreliability. It showed what a great platform it was, and everyone wanted to use it. At the same time, it was great for events, but it wasn't all that reliable. And so if we peek under the hood of Twitter in 2010, it was one big service, for the most part, called the monorail, the monolithic Rails application. And there are about, I don't know, a couple million users and a couple million tweets per day. About 100 plus engineers at the company, maybe 10 or 20 of which were in operations. So there's one deploy team managing every deploy at the company, making sure things go out. If things don't go out, they all get rolled back together. So it was and everything got rolled back, basically. So it was hard to move quickly, let alone at all. And we were down all the time for various reasons. Really, we were down several times a week, just full down, sites down. Everybody's pulling their hair out. But we were growing quickly. And so the engineering leadership got together and really identified that this was a real problem that we had to fix. One, we had no real reliability story. It was kind of a mess. And two, we weren't very flexible. We couldn't move quickly. Teams couldn't ship features. We couldn't actually grow the business and add all the things that we have on Twitter today because it was broken all the time, so we couldn't move. So we realized that we needed to really think about building a platform internally, to build an infrastructure layer that other teams can work on without having every operational detail impact them. And the other thing was that we needed to embed the ownership model in a much more concrete way, which is what DevOps, I assume, means. And we were using this dirty word SOA Now, I hear it's microservices. That's very cool. But what that means is that we wanted services that were owned by one team. They could make all of the decisions related to those services, deploy schedules, on-call rotations. All of that can be much less monolithic and distributed so that we can move independently and move quickly. So I want to, before I go into more of the details, I want to start with one of the overriding principles. This quote is actually from the FinagleCon keynote last year from Marius. Resilience is an imperative. Our software runs on truly dismal computers we call data centers. Besides being heinously complex, they're unreliable and prone to operator error. Now think about this for a second. If we could go back and run Twitter on like one huge computer, and we gave it perfect power and perfect cooling, and all its hardware components were perfect and would never break, we would do that. Right? That would be ideal, as we'd have a huge mainframe and it would never fail. But it's really expensive to do that. These computers basically don't exist. And so what every other company does now is they buy warehouse computers, they buy cloud resources, and you have all this commodity hardware, and it's going to break at some point. And we have to deal with that in our application because we can't rely on the hardware to do that for us. And so if we think about this for a second, especially in the cloud world, this means that a kernel you don't even know exists, a VM layer you don't know exists, a container layer you don't know exists, who knows what the networking topology is. All of these things are out of your control as an application owner, and we still have to do business. So when we hit a kernel bug in the middle of the VMAs or the Super Bowl or the election, hopefully people can still tweet and exclaim whatever they want to exclaim. And so this is a real challenge, an engineering challenge that we had to face. And now you really don't see the fail well anymore. So I want to kind of talk through a bunch of the failures I saw. These are not all of the failures Twitter saw. There's a lot more people that can talk about other things. This is from my perspective on the platform team. So in 2011, we started investing in a project called Mezzos. Has anyone heard of Mezzos here? Is anyone using Mezzos here? Excellent. And so Mezzos' idea is that we don't have to worry about the hosts. We can just have a layer that sits over all of the hardware. And so that as an engineer, I'm not memorizing host names as SSHing into things and doing curl deploys and things like that. I just want Mezzos to deal with this so that when a host fails, there's no fire drill. And also, there's another piece of this Aurora, similarly Marathon, there's other schedulers. These sit on top of Mezzos and make sure that the configuration is managed. So I can describe my service in a predictable way, deploy it, and it all works. And that kind of looks like this. So we have hosts down at the bottom. I have this Mezzos layer that manages host resources. And Aurora deals with services. So I can say I want a user service with 300 instances. Go run these. I don't care where they run. They just get run in the data center. And so as a service owner, I just focus on the top. I don't have to worry about most of the details about the bottom. This means that when one of these things catches on fire, as is known to happen, only this team has to be involved. We don't have to have a fire drill throughout the whole organization. And in fact, there's a great anecdote. In, I think, 2011 timeframe, we hit a kernel bug where if a host was up for 396 days, system load would go up to 1,200%, wouldn't schedule any work on the box, everything would just kind of melt down. And so we had a huge spreadsheet of uptimes for all of the hosts we owned. And as we started getting close to 360 days, we'd have to kind of schedule a fire drill and say, OK, this team has to move all of their software off of this, and we have to have a scheduled maintenance and a downtime and all this stuff. And it just touched every team at the company in like waves of pain. And so this, I think, is what really motivated internally and sold the engineering teams on why something like Mezzos was important, because we didn't want to have to worry about this sort of stuff. We wanted to focus on features. And so once we're in this nice, distributed orchestration world, we have this problem of service discovery. Has anyone had to deal with a service discovery scheme of some sort? And so this basically amounted initially to us putting Zookeeper clients in every single service of the company. And this works by, at startup, the user service will just announce itself. And it'll create a node and say, hey, I'm running over here. If you want to send things to the user service, I'm ready to take those requests. Same time, a client is going to set a watch and say, hey, I want to send something to the user service. Where do I send this? And so this replaces DNS and a whole bunch of other schemes that can be used to manage this. When we're in this world where things can be scheduled anywhere, we need a way that's kind of very dynamic and reliable to detect this stuff. This is all well and good. I can now send a request, an RPC or a thrift message or an HTTP call to the user service. Great. We have a highly distributed lock store to do this. Super reliable, right? No. I was on call for the service discovery for a long time, so I have some pain around this. Zookeeper goes down. Hopefully never, but it will. And when it will, it'll hurt. And so we have this big uh-oh moment. Zookeeper goes down, and nothing's sending requests, no traffic in the system. What do we do? Well, the first easy thing is, well, maybe if Zookeeper goes down, we don't have to just go out to lunch. I can keep the results I had previously in the client side and continue to serve requests. OK, now when Zookeeper goes down, system's still up and running, we're good. Now we ship that feature. A few months go by, and we're very happy. Any problems here? Well, of course. When Zookeeper comes back up, when it's been in an incident, if all of these servers can't register in time, and when we're back up, this might take a couple minutes or even longer, everything's reading empty results from Zookeeper. So Zookeeper's up, and it's saying, yes, I know the user service has nothing in it. And everything at the company is just sending traffic nowhere. This was probably one of the more painful outages I was ever involved in. And then when we fixed it, it took, I would say, months to get everyone to upgrade it and get the library out there. Because this is, again, all Zookeeper clients in every application that have to be upgraded across 100 teams or whatever. And so we started to think fundamentally about the APIs for service discovery. And we treated them more as advisory, so that we only treat additions from service discovery, and we treat them as something that might be available. And we rely on load balancers in the client to be smarter and keep things around until we can actually send requests there. So this is a kind of novel learning we had, but it took staff years, I think, to really get this right. And so now we have a connection between our services, and I have some way to send traffic between them. This kind of gets us to where Finagle starts. So Finagle, as you all well know, is an RPC library. It's asynchronous, it's functional, it's strongly typed, and it's pretty well battle tested. This started being developed in 2010 by a team on the front end at Twitter. And then within a year or two, every service at Twitter was using this, because we were all inventing these solutions to the same problems over and over again. It was a huge waste of time for most of the org. I was implementing load balancing, connection pooling, and timeouts and retries in Python. Somebody else was doing this in another language, Netty, Jetty. Every framework had the same sort of problems being solved. And so Finagle came through as the one solution that we could all kind of implement around. Finagle fundamentally is a session layer framework. It can be used to build things like Finch, which are kind of higher level concerns here. But the way I think about this is that the application code, your code should not be talking about how do I format a request and put it into a load balancer and worry about a bunch of the operational details. It should be focused on tweets and users, or bike rides, or cancer, or whatever the nouns in your domain are. Down at the bottom of the stack, we have all our hardware and cloud providers and the orchestration systems. And really, I think this gets us up to service discovery here, where the job of the data center is to get your process running somewhere and listening on a socket. The job of your application is to just receive domain events and do some things with them and do something else, right? Send some data store, return some response. And this middle layer is something we haven't really talked about too much in the past. The RPC layer, the session layer especially. This is really where Finagle comes in. And while we have this nice functional programming model, there's a lot of operational benefit we get here. And I want to talk about some of the benefits we get there. This is a great quote from a former Twitter engineer, Jeff Hodges. It's slow is the hardest problem you'll have. It's down is generally easy, right? Move things away off that box, bring it back up, get the connections established again. It's kind of a binary thing for the most part. It's slow can be a lot harder. So when the CEO comes down and says, well, when Kim Kardashian tweets, I can't see it for 20 minutes, what's going on? It's like, well, I see it. Well, I don't know. How do I debug this? Right? This works for me. And this is kind of where Finagle really, I think, shines. So first and foremost, before we worry about any reliability concerns, we need some way to measure things. We need visibility out of the system. Finagle is instrumented with stats, so we get counters, number of failed requests, number of successes, number of retries. We have histograms, especially for latency. so I know a distribution of how long things take. And then we have some tracing system. So Twitter open sourced Zipkin in, I think, 2012. This is an actual tracing diagram from Twitter in 2012. It's very complicated. This is the user service down here, and so we see how much connectivity there is between things. And the reason we can't do this just through a spreadsheet or through some other system is because these things change all the time. I may take in a new library and not even know what services it talks to. And so when I'm in an incident, I want to be able to go to one place and say, show me what's actually happening in the system right now, descriptively. And so with Finagle, this is all instrumented, so Twitter engineers don't have to make these decisions themselves. They get this tracing just by using the library. So once we have this kind of distributed, connected system, we have a whole bunch of latency type of problems to think about. And so the first thing we tend to do is think about timeouts and retries. Timeouts being an SLA, and retries being some amount of grace to recover. And so typically, we have 3 or 4 teams here. They all kind of agree on what the SLAs are for the service. Maybe we have to serve requests in about a second. And so we pick timeouts that kind of fit that. Anyone see any problems here? These things don't compose at all. Timeout up top is really the only one that matters. If anything, timeouts and retries below, the timeout up top is going to fire, and it's just not going to matter. So these things are actually really hard to do across a larger organization. You might be able to get these 3 teams to sit together and agree on timeouts. But when I have multiple paths through the system for different features with different timeouts, this becomes combinatorially hard to figure out. And so we change our approach. Instead of using something simple like timeouts, we move to deadlines. And the way that we do this is up at the top of the system, hopefully at the feature level. When a request comes in, we say, this needs to be served by this time. Then as we go down the system, I can simply look and say, is this timed out? Do I actually think I have enough time to solve this, to answer this question? And if I don't, I can just not do the work. And this becomes a much more composable thing where I don't have configuration at every level of the stack to deal with this. That brings us to retries. So we typically start with some number of retries. If it times out, if it fails for some obvious reason, let's just try it again so we can get the job done. So we say maybe retries 3, maybe we set a back off to leave some time between retries, or some jitter so they're not all lockstep. Any problems with setting retries like this? Well, what I've done is when the system's not healthy, I've made an error cannon. When we're failing requests, I'm going to put more load on this system. This is a terrible failure mode. This is the way to melt your downstreams. You're just never, once it's failing, you're just going to keep putting more work on it. It's never going to recover. So Finagle took the novel approach of thinking about this in terms of budgets. How much more load am I willing to put on the system below me to satisfy the request? And so we now in Finagle can say, I want a 20% retry budget, and that limits the upper bound of work I'll do when we're in an incident. And so this gives us a nice mechanism for load shedding. That brings me to load shedding. And so when we do something like a timeout, right, we cancel a request here. There's still work going on downstream. They're doing database reads, and maybe they're hitting many services, and this is a big fan-out query. And that's expensive. When we're in an incident and we're timing lots of things out, we still have lots of excess work that we're never going to use results from. And so we need a way to harvest that out of the system, reap that. And so this is done through a mechanism of cancellation. We can, if a client times out, it can inform its downstream and say, hey, I'm not going to get the result of this. I don't care. Do whatever you want with this. You can keep doing the work. You can fail it. I don't care what your answer. And this allows us to tear down connections or tear down pending requests and really harvest a lot of load when we're in one of these incidents. Similarly, backpressure is, I think, a very interesting thing to think about. So let's say we have lots of requests coming through the system, but down in the database layer, maybe we have a lock intention or something that's acting just generally slow. What's going to happen in the user service? Well, if it's written in the JVM, it's going to go into garbage collection, and it'll never recover. Right? We're going to have so much memory pressure coming into this thing. If it's holding on to thousands of requests that it can't satisfy, it'll just melt. Furthermore, you won't be able to stand it back up because it'll just crush into the load during restarts. And so we need to think, melt, yeah. And we need to think about how we can limit this and constrain this so that we actually press back up to the client so that the clients can make better decisions, whether they go to another data center, whether they relax their polling cycle and ask for less data. And so we do this in a simple protocol like HTTP1. We do this simply by not reading. If I don't read from the socket, TCP will handle the backpressure for me. We just need a way to be principled about not reading from the thing until I've sent the response upstream or downstream. In HTTP2 and MUX, which are multiplex protocols, we actually have explicit flow control mechanisms to acknowledge the amount of request data per, or data per request to satisfy the backpressure. This is, again, another very, I think, overlooked piece of what it means to have a well-conditioned system for incidents. Finally, I think one of the things Finagle really shines out is load balancing. And this is maybe the sharpest tool for reliability we have in Finagle's tool belt. If you are familiar with other load balancers like Nginx or HA proxy or hardware load balancers, these tend to operate at the connection level. And so they can only do things like round robin. For every connection I get, I send it to a new host. Or I can use a queue depth one and say, OK, I'll establish a connection to the host with the fewest connections. This is actually a very naive load balancing strategy, especially when we're dealing in request responses, when I'm not dealing purely in streams. So Twitter, over years, moved off of these naive load balancing algorithms to per request level load balancers like Yuma. And so what Yuma does is it actually looks at the latency of every request. How long did it take for me to get a response to this, to each node, and punishes slow nodes. So that when a node is maybe starting up and needs to warm up, we send it less traffic than we do the other nodes. It doesn't get an equal amount. Or if it's just going to garbage collection, we can ease memory pressure by not sending it as much work. Another load balancing algorithm called Aperture is, I think, also pretty novel. If you're talking to a large cluster of 1,000 nodes and you're doing 10 requests a second, it's going to be very hard to make smart load balancing decisions because you don't have waiting information for the vast majority of the endpoints. And so what Aperture does is it constrains the number of hosts you consider to fit your load size. And so as I get more load, I consider more hosts to load balance over. And this actually leads to much better performance results for some services. This example here shows us that really how much of an impact these load balancing things can make. And so if we have a 1-second timeout and I'm talking to a 10-node cluster, and one node of these starts to fail that timeout, with a round robin or fewest connections scheme, this pushes us into a 95% success rate. In most of my on-call rotations, that's been a wake me up success rate, and I don't like to be woken up. So just by moving to a Yuma balancer, we can push this over 3 nines, which is usually a sleep through the night success rate, I hope. And that's just by changing this one parameter in a Finagle client. It's a really amazing difference. This is a quote from a speaker at FinagleCon last year. Phil Coccato was at DigitalOcean and SoundCloud. And I think there's a lot of truth to this. Any sufficiently complicated microservice architecture contains an ad hoc, informally specified, bug-ridden, slow implementation of Finagle. So I know you're all Scala people. So yeah, just rewrite everything in Finagle. You get all this stuff, and you can sleep through the night. Well, unfortunately, we also have some things that aren't written in Scala in the world. Or maybe we don't have Finagle as an option because it has a bunch of programming implications. Well, I've been working on this project called Linkerd for the last year or so. It's open source and on GitHub. And the idea here is this is a proxy version of Finagle. So it's written in Finagle, but it exposes just ports. You send a request into these ports, and we deal with a lot of this complicated management layer, the management of requests. So backpressure, timeouts, retries, all of these things. It's very pluggable. Protocol support's pluggable by default. HTTP and Thrift are there. We've just added HTTP2 support in the last couple of weeks. We support a number of discovery and orchestration backends. And anything you want to be pluggable probably can be pluggable in it. And that just requires usually writing about 100 lines of Scala or so. Why are we called a linker? Well, the idea of a linker is not a new one. We have abstract names, and we want to bind them to more concrete names, usually addresses to send requests to. And so we can take this approach to service discovery and naming. In a complicated system, you may have, let's say I own the user service. when a timeline service wants to send to the user service, which version do they send to? Or if I own the user service and I want to deploy a new version, how do I get them to test against my version? Well, this can be very complicated in a large organization. You maybe have a staging data center, and everyone tries to deploy there first, but nobody really wants to test there because it's not real production. It doesn't get real traffic. And it's actually hard to maintain a fake copy of your ecosystem. The other option, of course, is to just deploy to prod and pray, which is, we did a lot of that too. And there's actually a very nice happy middle via Finagle's naming system. And so what this allows us to do is to deploy a new version of the service and incrementally move traffic onto it, separately from the deployment phase. This idea of logical naming comes in where every client, and in Linkerd's case, every request is given some logical name that represents its destination. So for instance, the user service. What we really want it to do is route to some server set, some concrete cluster. So look in Zookeeper, in the prod namespace, and the user service, and resolve that. Or maybe the staging one. And we have this language for expressing rewrites. So I say, when you're looking at an S prefix, make it a Zookeeper prod lookup. And I can add overrides here that change that behavior in a very dynamic way. This can be used for things like staging. In fact, one of the last things I shipped at Twitter was a staging infrastructure like this. And so I can go into my browser, and I'll demo this if I have time at the end, and just add a header onto request and say, well, when you're going to talk to the B service, use the B2 service instead. This actually gives us kind of a dtrace style call intercept interface at the data center level instead of in the process. Similarly to this kind of redirect staging use case, I can also do proxies. So let's say I want to have a proxy that injects some application level failure, that returns a different data structure when certain things happen, or just injects latency or something like that. I can use the same rewrite rules to say, well, when you would go to the E service, go to the P service first, and then go to the E service. And this allows us, again, to do these kind of call intercept style things and filters to do either quick prototyping or failure injection or a number of use cases. And this brings us to what we kind of consider to be a service mesh. That we deploy Linkerd in a maybe per host mode. We have applications talk directly to Linkerd. And so we have basically Finagle as an out-of-process networking stack. And these can communicate. They can do protocol upgrades. They can do transport security. They can manage backpressure and cancellation and knacking, et cetera, et cetera. We use another system called Namerd to front service discovery, which manages most of these rewrites I've been discussing. And with that, I'd like to do a little bit of a demo. So anyone familiar with Job? Job is not very smart or classy. And he wrote a very inane program in the show Arrested Development. And so naturally, I took this program and I made it a microservice that runs in Google Compute Engine at a large scale, as you do. And so the way this works is we have a web front end. These are little Go programs. I have a word database, which is basically a dictionary of really dumb words. The web service calls that, gets a result, gives it to the gen service, and the gen service just repeats it forever or up to some limit. Pretty dumb. What we're going to do is we're going to deploy a new version of this, or actually of both of them. And we're going to use Namerd to manage how that rollout goes. Use this linking and naming system to control and do an incremental controlled deploy. I also will remind you that this is all open source and on GitHub. You can go through this demo yourself in about 10 or 15 minutes afterwards. So let me try to set up this. You hear me? OK, so here is my service. Like I said, it's pretty dumb. And here's Linkerd's dashboard. So this is the admin interface on one Linkerd process on the web front end. And we see here is that there's these two clients. Linkerd configuration really doesn't have anything specifically about that. I'll show you Linkerd's config. Basically has a DTAB or a policy that looks like this, which says, when you see an HTTP/111 request, look up the host name as a service in Kubernetes. I'm using a Kubernetes scheduler here. So there's nothing application configuration-wise about Linkerd. And we're sending a bunch of load through the system. I can curl it, and it all looks great. And so I can even, excellent. And so what I want to do is now I want to figure out, I want to stage my new services. I have these two growth hack versions of the service. And we're going to try to send requests through one of them at a time. So I'm just going to look up and so what this request says is I've added a header onto my request that says, when you would use the gen service, please use the gen growth hack service instead, if it exists. And I immediately get a different result, right? So this is now, if I go to just my normal old prod thing, I get the old result. When I add this one header, I'm talking to a new service downstream. This is propagated with a request, and I can do staging in this way. So now let's put some consistent requests. We see that we're getting different words back. And I want to go, I'm going to change the policy here. And so by default, we're just doing everything there. And what I'm going to do is say send 10% of traffic to each of the new services and 90% of the traffic to the old versions of the service. So weight with 1 to 9. And I am going to update. So this is, I push an update into nameRD, and linkerd immediately picks up the changes. And so we see here, we see there that now about 10% of the load is going on a new version of the service. And we see that we've just automatically detected new clients. I have success rate information, latency information, et cetera. We do see this weird thing here, maybe, that this new version of the service isn't so healthy. I may have written a bug into it, but we're going to pretend we didn't see that for a moment. Ignorance is bliss. And we now see in this thing that we actually get different results back. Now I'm getting about 1 out of every 10 is going to the gen growth hack service, and I get that very different result. OK, now what we can do, let's go, we're just going to go to production. We're ready for it. We didn't see the error. And what we're going to say here is use the growth hack versions of the service by default as long as they're there. If they don't exist for some reason, this or becomes a fallback to the old version of the service. I push the update, and I get the new results. And we see here that traffic shifted over. One interesting thing here is that we see higher load on this. So here we see they're even, right? Here I see one is doing more requests. Why might that be? I'll give you another hint. Here we see about 80% success rate on this client. Yet, at the high level, we're doing 100% success rate. Where is this failure going? Well, I gave you kind of a hint before. We're doing retries. And so we can look. We know these are GET requests because they're HTTP. And I can look at the response code and know it's a 500. And I can automatically retry those. And so here, this is just using retry budgets. And it happens to be that we have a retry budget of 20%. And we're failing 20% of the requests. So these just line up perfectly. And we're able to retry all the requests and improve success rate. Finally, we've acknowledged this. The ops team's freaking out and saying, the service isn't going well. What are we going to do? And so we're just going to delete it. I don't want to push new DTAB rules. Just going to tear it out of production. We tear it out. And traffic just falls back onto that new service immediately. There we go. So linkerd is about, it's been open source since February. It's still a pretty young project, even though we're standing on the shoulders of giants. We're using Finagle and Eddy to do a lot of the heavy lifting here. So we've just got HTTP2 in. I'm really excited about it. It's going to open up a whole bunch of operational features for us, especially gRPC. We're looking at all sorts of auth features, TLS client certs. I talked about deadlines. We're not enforcing them yet. We're just propagating them with requests, but not acting on them. We think we're in a really good place to do dark traffic, so I can just send requests to the new version of the service without returning the results to the client, and we can give you a little bit of a preview of what it might be like to deploy. And generally, Linkerd is just a configuration layer over Finagle. It's so that you don't have to write a new service in Scala to get all this value. You can just plug this into your application with a little bit of configuration and get the same value. And so there's a lot of stuff in Finagle that we haven't been able to expose configuration-wise. And we're looking for your help to figure out what the right APIs and user interfaces are for exposing this configuration. So with that, I'm going to ask you to go to linkerd.io. It's a very pretty website. I didn't make it. We have a Slack where we're always happy to entertain your questions. We have a GitHub page where we love people to click on the star. It makes us feel really good. And you can follow me on Twitter. I'm trying not to use it this week. You can follow Linkerd. And with that, I think we have a couple minutes for questions, potentially. I'll give you a sticker if you ask a question.
What is black traffic?
What is dark traffic is the first question. So dark traffic, in my mind, means I can send requests to a new version of the service, and the results of those don't go to the client. So I still send two versions of the request, one to the new version of the service, one to the old. And we can just compare the results, see the latency differences, see the differences in results, without impacting the clients at all. And it's a nice way to get confidence of a new version of a service before we go to production.
So what does the migration path look like for when you're integrating Linkerd into your services?
That's a great question. Hopefully it's very incremental. The idea here should be that you can do this in a one service at a time thing or just in some subset of the service and change the configuration of the client to instead do service discovery or talk to DNS directly, send its request to the local host of Linkerd. This can typically be done by setting an HTTP proxy environment that sends requests to the local host. But there's on Linkerd.io, there's a whole number of examples on how to set this up. All right, and I'm being given the crook. I'm being yanked off stage. I really appreciate it. Thanks.